Very good morning to all of you. We will continue with our discussion in the field of magnetostatics. Remember last time we started looking at magnetic fields and calculation of magnetic fields, etc. Now, before we started magnetostatics, we had discussed electrostatics, in which we said that a charge, a stationary charge is affected by an electrostatic force. So, if you have a charge, then it creates an electric field in the surrounding region, and if you put another charge here, that charge is either attracted or repelled by this electric field. So, depending on the type of charges, you can either have attraction or repulsion, and this force is along the line joining these two charges. So, that is electrostatic force. Now, in magnetostatics we look at magnetic field effects, and these magnetic fields are generated by currents. So, when you have a stationary charge, it has no magnetic effects, because the only effect is electric effects. So, if you have a charge which is stationary, even if there are magnetic fields, there is no force on the charge. The charge is affected only by electrostatic forces. When the charge starts to move, then apart from the electrostatic force, there is another force which is called the magnetic force. Now, if I have a charge which I make to move along a certain direction, I find that the force depends on the direction in which I am moving this charge. So, suppose I take a positive charge and move like this, there is a certain force acting on the charge. If I move in another direction, then the force is different. So, what I do is I vary the direction of propagation, and I find that along one direction of propagation there is no magnetic force. So, if I vary the directions, I will find one direction of propagation along which there is no magnetic force, and that direction defines the direction of the magnetic field at that point. And then if I vary the direction of my velocity vector, I find that when the particle is moving perpendicular to this direction of 0 force. So, for example, if the 0 force was along this direction, if I move perpendicular to that in any orientation, I find that the force on the charge is maximum. So, the force acting on this moving charge depends not only on the velocity, the speed of the particle, but also the direction in which the particle is moving. And so, we had defined the magnetic field through a relationship with the force. Just like electric field, we have defined a magnetic field. So, suppose you had a magnetic field which is represented by B vector like this, and if you move a charge in this direction, then you find that the magnetic force magnitude is q v times B. So, we had defined B as magnitude of force divided by q times V. So, this is 90 degrees, and so this is a unit called Tesla, that is 1 Newton per ampere meter. So, Tesla is a big unit, and we had also introduced another unit called Gauss, which is 10 to the minus 4 Tesla. So, this is the force acting on the charge. So, if the charge moves in different directions, then the force changes, and so we find that the force can be represented by a vector relationship F B magnetic force is equal to q times B cross B. So, if I have a coordinate system like this, so x, y and z, suppose I have a magnetic field oriented like this, and if my velocity of the charged particle is in this direction. So, suppose let me assume there is a positive charge moving in this direction, then the force is q v cross b, and if this is an angle phi, then the magnitude of the force, as you can see here, the magnitude of the cross product is q v b sin phi. It depends on this angle, and if phi is 0, then the force is 0, as we discussed before, that is the direction of the magnetic field. If phi is 90 degrees, you get the maximum force q v b. Also note the direction of the force. Unlike electrostatic forces which were acting along the direction of the electric field, either towards the direction of the electric field or oppositely, the magnetic forces are perpendicular to the magnetic field B and to the velocity vector. So, you must have studied cross product before. So, V cross B is a vector in this figure, V cross B is a vector in this direction. So, if the charge is positive, the force has the direction of V cross B, and as I mentioned last time, I must use the right hand rule. So, I take my right hand and move my 4 fingers from B to B, and the direction of the thumb represents the direction of the force. So, I get this force along V cross B here, and the magnitude of the force. So, unlike electrostatic forces, magnetostatic forces are perpendicular to the velocity vector as well as to this magnetic field direction, and that defines my force on the moving charge. Also note that if q is negative, the force is opposite in the opposite direction, it is at the direction of minus V cross B if q is negative. After we had discussed this, we introduced Biot-Savart law, which will tell us what is the magnetic field produced by current carrying conductors. So, if you have a current carrying conductor like this, suppose the current is propagating in this direction. So, I take a small elemental length dl, the direction of dl vector is along the current direction, and if I have to calculate the magnetic field at this point, I draw a vector joining these 2 points, the current element idl and the position here r vector. So, the magnetic field dB because of this current element dl is mu naught by 4 pi I dl cross r by r cube. We have discussed this before in the last lecture, that the magnetic field generated by this current element dl vector, I dl is the current element here at this position p, whose coordinate with respect to this is r vector here, then the magnetic field generated by this is represented by this equation. Mu 0 is the permeability of free space, and as a value 4 pi 10 to the minus 7 Tesla meter per ampere. We are also seen that epsilon 0 mu 0 is 1 by c square, where c is the velocity of light in free space, speed of light in free space, and so epsilon 0, which is the dielectric permittivity of free space, and mu 0 the magnetic permeability of free space are related through this equation epsilon 0 mu 0 is equal to 1 by c square. So, this gives me the magnetic field generated by a small current element, and just like electrostatic fields, the magnetic fields also satisfy superposition principle. So, if I want to calculate the total magnetic field generated by this entire element of current here, I have to calculate the current, I take individual current elements at different points and calculate the magnetic field generated by each individual current element, add them up at this point vectorially and get the total magnetic field. So, in fact, last class what we had done is to calculate the magnetic field due to a circular loop of current. So, let me recall, we had taken a loop like this, I can call this z, this is x, this is y, and let me assume a current is flowing like this. So, we try to calculate the magnetic field along the axis. To get a simplified expression, we can get analytical expression for magnetic field along the axis by using Biot-Savart law. So, we started looking at it. So, what we need to do is, if this is the point P, I need to consider different elements of current here, 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 etc., and integrate all the current elements, the magnetic field produced by all current elements at this point, and calculate the total magnetic field. Now, we had used some physical arguments to show that for every element here, there is another current corresponding element on the other side, which produces a magnetic field whose x components cancel. Now, I want to show this a little more rigorously here before we move on to the next problem, and let me do the following. So, let me draw a figure now which corresponds to the xz plane, the plane xz, and let me draw a figure here. So, this is x axis here, this is z axis. So, remember, the current is coming out of the paper here and going into the paper on the other side. So, if I extend the x axis in the backward direction here, so the current is coming out from this direction and current is going back. So, current is moving in the y direction here and minus y direction here. So, I will draw corresponding arrows here. So, this is a point in the center of a circle, means the arrow is pointing up, which means the current is coming out of the paper. Here at the same distance on the other side, I will plot the end of the arrow, and that is the current going towards the into the page of the paper, and this is the radius of the current loop. So, this is the radius of the current loop, capital R, and so this is the XZ plane, and my problem is to find out the magnetic field at this point P. So, this as you can see here, this has coordinates 0 z, and this has coordinates so r 0, and this has coordinates minus r 0. X coordinate is r, z coordinate is 0, there is no y coordinate, I am in the XZ plane. Similarly, the x coordinate is minus r here, and the z coordinate is 0. So, let me try to find out what is the magnetic field generated by this small current element at this point. So, I have a small element of current coming out of the piece of paper, and I draw this vector r. Now, as you know, I have this equation Biot-Savart law, dB is equal to mu naught by 4 pi I dl cross r by r cube. So, I need to calculate, I need to know dl vector and r vector and the distance r to be able to estimate the magnetic field produced by this current element here, and I will show you that if I calculate the magnetic field because of this current element and this current element, one of the components gets cancelled, which we argued last time through a discussion, but I would like to show you explicitly. Now, for this, what is dl vector? Dl vector, remember, is pointing along the y direction. So, the y direction is coming out of the plane of the paper, and so dl vector will be j cap into dl, small element, and j cap because it is along the y direction, and r vector is the coordinate of this, because the vector joins from here to here, r vector is the coordinate of this point minus the coordinates of this point. So, I will have minus r I cap plus z k cap. Z k cap is the position of this point, and minus r I cap is the coordinate of this point. So, the difference is r. So, dl cross r will be equal to j dl cross minus r I cap plus z k cap, which is equal to now. So, minus r dl j cap cross I cap is minus k cap. So, this becomes plus k cap, j cap cross k cap is I cap. So, plus I z I cap z dl, j cap cross I cap is minus k cap, with a minus sign becomes plus here, j cap cross k cap is I cap, which is z dl. So, because of this current element, this one, the magnetic field produced at this point dB, let me call it dB1. So, this is 0.1 and this is 0.2. So, I want to calculate what is the magnetic field here because of this small current element at this point 1, and what is the magnetic field here because of the small current element 2. So, because of 1, I have mu naught by 4 pi I. So, dl cross r is r dl k cap plus z dl I cap by r cube. R is this distance from that point to this point. So, that is the magnetic field produced at this point. It is a magnetic vector field. As you can see here, it has both the z component and the x component, both are positive. So, it must be pointing like this. This B vector must be perpendicular to this dl vector and the r vector, because this is the equation. So, B vector is proportional, this is the dB vector dB1. So, dB1 vector is perpendicular to r vector and to the dl vector. Now, let me calculate because of the second element. So, let me draw the figure again here. So, I have this element here, and this is the point P. So, now I have to draw this vector. This is my r vector now, and now I must, so again I must use this equation dB vector is equal to mu naught by 4 pi I dl cross r by r cube. Now, dl vector is equal to Now, please remember the current is flowing into the page. So, this is my x axis, this is my z axis. So, y axis is coming out of the plane and the current is going into the plane. So, this is minus j cap d l. Here it was plus j cap d l because the current is coming out in the y direction. Here the current is going in the minus y direction. So, d l vector is this, and r vector is equal to, again the coordinates of this are 0 z and the coordinates of this are minus r and 0. So, r vector will be k cap z plus r I cap. So, d b 2 will be equal to mu naught by 4 pi I. So, now I must calculate d l cross r. So, let me calculate d l cross r separately. So, d l cross r is equal to minus j cap d l cross k cap z plus I cap r, which is equal to, so minus j cap cross k cap is plus I cap. So, minus I cap d l into z, j cap cross I cap is minus k cap. So, plus k cap r d l. So, let me rub this off. So, I have d l cross r vector minus j d l cross j k z plus I r, j cap cross k cap is plus I cap. So, with the minus sign here, and j cap cross I cap is minus k cap. So, that becomes plus. So, that is d b. So, I can calculate d b 2, the magnetic field produced by the second element. So, d b 2 is mu naught by 4 pi I into minus I cap z d l plus k cap r d l divided by r cube. And let me recall what we had for d b 1. So, d b 1 vector is mu naught by 4 pi I z d l I cap plus r d l k cap by r cube. Please remember that small r is the distance of this point from the current element, and because I am on the axis of the current loop, this distance is equal to this distance. So, small r is the same both in the d b 1 formula as well as d b 2 formula. The only difference between these two is the current element here it is coming up, here the current element is going down, the r vector is here, and in the other case the r vector is this r vector. So, the r vectors are different in the two cases. Now, you can clearly see. So, let me draw the figure again. So, I have this z x. So, this is coming out, this is going in. So, at this point, so this is one r vector, this is another r vector here. So, as you can see here, d b 1 is the magnetic field produced by this current element at this point, d b 2 is the magnetic field produced by the diametrically opposite current element at the same point, and you can see here the x components are exactly equal and opposite and they cancel off, and x component is nothing but the component perpendicular to the z axis. Z components add up and x components cancel off. This is precisely what we had discussed in the last class. I had said that this produces a magnetic field like this, d b 1, this one produces the magnetic field like this, d b 2. Both of them are at the same angle, they have the same magnitude of x component, but opposite, and so cancel off and the z components add. And you can see here by a simple calculation, with a very simple calculation using vectors, we have found out that the x components cancel off and the z components add, and so I will get the total magnetic field that is generated at that point by the two elements d b vector is equal to d b 1 vector plus d b 2 vector. So, d b 1 vector is the magnetic field produced by one current element, d b 2 is because of the other current element. So, if I add these two quantities, x components cancel, z components will add up, and I will get mu naught by 4 pi I into 2 r d l k cap by r cube. So, you can see the magnetic field is along the z axis. Now, if I go back here and look at this. So, what I have shown is the magnetic field produced by this current element and this current element are cancelling off their components perpendicular to the axis. Similarly, a magnetic field generated by this element and the diametrically opposite element on the other side will have cancelled their components perpendicular to the z axis and so on. So, all these components will cancel off, resulting in a total magnetic field only along the z axis. So, I can calculate total magnetic field is equal to mu naught I by 4 pi into 2 r by r cube. Now, small r is this distance, smaller is this distance, this is capital R, this is z. So, small r is nothing but r square plus z square, the square root. So, this is r square plus z square raised to power 3 by 2 into k cap into integral dl. Now, I have to be a little careful, because in deriving this equation I have taken account of both these elements, diametrically opposite elements. So, integral over dl must be in a semicircle, because the upper half semicircle and the lower half semicircles are exactly cancelling their normal components. So, this will be in a semicircular arc only, this is semicircle, and over a semicircle the length is nothing but, so mu naught I 2 r by 4 pi into r square plus z square raised to power 3 by 2 into this is pi r into k cap. So, this is nothing but mu naught I r square by 2 times r square plus z square 3 by 2 k cap. So, that is the magnetic field, and if you go back to my last lecture, you will find that we had derived the same equation for the magnetic field of a circular loop of coil, circular loop of current carrying conductor along the axis. This is along the axis, please remember this is not at arbitrary points. So, let me draw the figure again. So, this is my loop current carrying current like this is z axis, x and y. So, this along this here the magnetic field is along this direction, and here the magnetic field is along the same direction here. Please remember the magnetic field is along k cap direction, and this is along the axis, and as this equation shows, the maximum magnetic field appears along at the point z is equal to 0, where you get the maximum magnetic field. And last time we had drawn a figure showing the magnetic field variation with position, and it goes like this. This is magnitude of magnetic field versus z, and that is the magnetic field. So, at this point B max is given by mu naught I r square by 2 into I put z is equal to 0. So, you get r cube, which is equal to mu naught I by 2 r. That is the magnetic field at the center of the circular loop of current, and if I put vectors here, k cap, is k cap here. Okay, so, let me draw. So, this was the magnetic field along the axis. We have not been calculating magnetic field elsewhere, but let me just draw a figure which you will which if one were to calculate magnetic field at all points, you will get a figure something like this. So, I have the current carrying conductor here, circular loop. So, I will have one magnetic field line coming like this, there is another line coming like this and going like this, then another line coming like this going here, here another line coming like this going off, closing off. So, you have magnetic field lines which are going in one direction and they form circular loops. So, these loops actually go for a long distance and come back and close on each other, and so this magnetic field distribution because of a current loop is very different from charge distribution, electric field produced by charge distribution. Also notice that we have to use the right handed screw rule to find out the direction of the magnetic field. So, the current carrying conductor is carrying a current like this. So, as we have seen last time, if the current is flowing like this, then the right handed screw will move towards me, and so the magnetic field direction is towards me. So, a current going like this will generate a magnetic field like this, a current going like this will generate a magnetic field in the opposite direction. Now, there is something which is interesting which I can get from this equation. So, let me recall this equation here, the magnetic field equation. let me rewrite this equation. B is equal to mu naught I r square k cap by 2 times r square plus z square raised to power 3 by 2. So, let me look at distances which are much greater than the diameter of the loop. So, B will be mu naught I r square k by 2 z cube. So, I multiply and divide by pi. So, I can write this as mu naught I pi r square k cap by 2 pi z cube. I multiply and divide by pi. Now, what is pi r square? Pi r square happens to be the area of this loop. R is the radius of the loop and pi r square is the area of the loop, and the loop is carrying a current like this, and this is my direction. Remember, some lectures ago we had introduced the concept of vector area. So, if I have an area, I can define a vector area, and here I define the vector area according to the right hand screw rule. So, if I have a current carrying conductor like this, then the vector area is here. So, I define the vector area as A is equal to pi r square area into k cap. So, this is the z direction which I have chosen, that is the vector area. So, I can define the magnetic field as mu naught I vector area by 2 pi z cube. Now, while doing electrostatics, I had introduced the concept of electric dipoles. So, let us recall that if you have a negative charge and a positive charge, we can define an electric dipole moment which is q times d, and it is in the direction of this from negative to positive. So, let me call this, so this is z axis, this is z cap, k cap. So, that was the electric dipole moment. I can also define a magnetic dipole moment m by current into area vector. So, if I have a current carrying loop here, so this is area vector. So, this is the magnetic dipole moment, current into area vector is called the magnetic dipole moment, and so if I use that equation here, I will get the magnetic field produced by this current loop on the axis far away is mu 0 m by 2 pi z cube. So, this is for z much greater than r. Remember, we had also calculated the electric field produced by an electric dipole far away from the dipole, and we had obtained an equation for the electric field. So, electric dipole E is equal to P by 2 pi epsilon 0 z cube for much greater than A. So, I will call this plus and this is minus, and this we had called 2A, and P was the dipole moment, and this is for distances large. So, this is z axis, this for z distance is large compared to the size of the dipole, and for the magnetic dipole moment, for the magnetic field we have a similar relationship, except that instead of 1 by 2 pi epsilon 0 we have mu 0 by 2 pi here, and instead of electric dipole moment you have magnetic dipole moment here, and instead of both of them go down as z cube. So, the field reduces as the cube of the distance from the dipoles. So, we will come back to looking at magnetic dipoles and torques and forces on magnetic dipoles, but before that I just want to draw a figure to show you the difference between the two dipoles, dipole fields. So, let me draw electric dipole here. So, if I have a plus charge here and a minus charge, the field lines will be looking like this. We had seen this before. the field lines start from positive charge and negative on the and end on the negative charge. So, all the fields are starting from the positive and ending on the negative. For the magnetic dipole, the field lines are very different. So, magnetic dipole, I have a loop of current. So, I am taking a loop like this. So, magnetic field lines will be, this field line will start from here. So, look at the dipole fields are very different. Here all the electric field lines are starting from the positive charge and ending on the negative charge. Here the field lines have no beginning or end. So, they are loops, they are continuous loops and they do not have start from anywhere and end anywhere. So, that is the reason why there are no corresponding magnetic charges unlike electric charges. We have electric charges positive and negative and you can find an individual separate charge, you cannot find an individual magnetic charge and there are no magnetic field lines starting from some point and then ending at another point. All the field lines are closed on each other and this leads to, as we have seen before, a Gauss's law for a magnetic field which is integral B dot dA. So, the flux of magnetic field through any closed surface will be 0. So, if you take any surface here, suppose I take a surface like this, as many field lines will enter as will get out from here, because there are no individual charges, there are no starting points and ending points here, there will be no flux of total flux of magnetic field will be 0. So, that is the Gauss's law for magnetic fields and this is the corresponding difference between electric field and magnetic fields. So, please note that the two field lines are very different here, one is starting from positive ending on negative, the other one are closed loops. So, that is a magnetic dipole here and that is an electric dipole. So, now I want to look at another problem, another example from where we will derive a very important relationship later on. So, this is an infinitely long straight current carrying conductor. So, I want to find the magnetic field due to an infinitely long straight current carrying conductor. So, I have a current carrying conductor like this and I want to find the magnetic field at this point, some point P and so this is my point P where I want to find the magnetic field and that is an infinitely long current carrying conductor. Remember in electrostatics we had also calculated the electric field due to an infinitely long line charge. Similarly, I have an infinitely long current carrying conductor from which I want to find what is the magnetic field at the point P. So, I will use Biot-Savart law, write down the electric field at P due to a small element of current and using superposition law, principle of superposition, I will add the magnetic field due to all current elements at this point P and get the total magnetic field. So, for this what I do is let me assume that this is my x axis and this is my y axis and I take a small current element here dy and this is my point here and I join this. So, let me assume that this distance is x and this distance is y. So, I take one current element at a distance y from this perpendicular point here. So, that is my xy axis and I want to calculate the magnetic field at this point because of dy. Again I will use Biot-Savart law, dB is equal to mu naught by 4 pi I dl cross r by r cube. Now, you see here that dl vector is always equal to, is along the y direction, the current is flowing like this, I am assuming current is flowing along the y direction. So, dl vector is dl times j cap, it is along the y direction. So, all current elements wherever you take along the straight path of the current, it is always dl times j cap and r vector is equal to the coordinate of this point minus coordinate of this point. So, this point has coordinates x and 0 and this point has coordinates 0 y. So, I will have the this will be x I minus y j. X I is the, or this vector from here to here is x I, and from here to here vector is y j. So, this vector minus this vector gives me this vector. So, this r vector is like this. So, d l cross r is equal to d l j cap cross x I cap minus y j cap, which is equal to, so j cap cross I cap is minus k cap minus x d l k cap, and j cap cross j cap is 0. So, d l cross r is minus x d l k cap. So, d y sorry d l, okay, that is fine. So, d l is nothing but small element d y. So, let me write this as minus x d y k cap. So, please note here that every current element, no matter what value of y you take, is producing a magnetic field along the z axis minus z. So, the z axis here you see I must use the right handed coordinate system. So, x is here and y is here. So, x z is coming out of the paper, and what this says is d l cross r is minus x d y. So, that means the magnetic field must be pointing into the board, and that is expected because remember right hand rule, if my current is flowing like this, it will generate a magnetic field in this direction. So, it just so happens that all current elements along the length of the wire are producing a magnetic field all pointed along the z direction. So, I can simply add the total magnetic field produced by all small current elements to get the total magnetic field. So, let me write an expression for dB is mu naught by 4 pi I d l cross r by r cube, which is equal to mu naught I by 4 pi. So, d l cross r is minus x d y k cap by, now what is the magnitude of r? X square plus y square is r square. So, this is nothing but x square plus y square raised to the power 3 by 2. So, the total magnetic field will be equal to minus mu naught I by 4 pi. Now, x is independent, x is this distance from here to here, that is independent of my integration variable. So, x comes out, x integral dy by x square plus y square raised to the power 3 by 2 and into k cap. So, if I had a current carrying conductor from a coordinate y 1 to y 2, I can find out the magnetic field produced by a finite length wire and then let the limits go to infinity. So, let me assume that I am taking a finite length of wire lying between y 1 to y 2, y 1 is the coordinate of this end, y 2 is the coordinate of this end, and this is the length, y 2 minus y 1 is the length of the wire, and I want to find the magnetic field produced by this length, this small length of the wire, and so I will have an integration from y 1 to y 2. And that is a simple integration. All you need to do is to use change of variables. So, if I call this as phi, you note here that y is equal to, so y by x is tan phi. So, y is equal to x tan phi, dy is equal to x secant square phi d phi, x square plus y square is equal to x square into 1 plus tan square phi, which is equal to x square secant square phi. So, I can substitute all this into this equation and find an expression for the current. So, B is equal to minus mu naught I by 4 pi x integral x secant square phi d phi divided by x cube secant cube pi. Remember, this is x square plus y square raised to 3 by 2 here. So, I have x cube. So, this is equal to minus mu naught so there is a k cap minus mu naught I by 4 pi, there is x square and I get x here, integral 1 by secant phi d phi is cos phi d phi k cap, which is equal to minus mu naught I by 4 pi x, this is sin phi between the two limits. So, let me call the two angles. So, let me call the two limits as phi 1 and phi 2. So, sin phi 2 minus sin phi 1. Now, what is sin of the phi? Sin phi is nothing but y divided by this distance. So, sin nothing but sin phi is nothing but y divided by x square plus y square raised per half. So, sin phi 1 is nothing but y 1 by x square plus y 1 square raised per half, and sin phi 2 the other limit is equal to y 2 by x square plus y 2 square half. So, these are the two limits and I get so this is a k cap here. So, the magnetic field is nothing but given by minus mu naught I by 4 pi x. So, y 2 by square root of x square plus y 2 square minus y 1 by square root of x square plus y 1 square k cap. So, that is the general expression for the magnetic field. So, I have a current carrying conductor. So, this is so this at some point I am calculating. So, this is my y axis here, x axis here I am calculating at this point. So, this has coordinates y 2, this has coordinate y 1. So, finite length wire. So, there is a wire of finite length carrying a current like this, current I. Now, I can take the limit. So, this is for a finite length of wire. I can actually, if the wire becomes infinitely long, y 1 tends to minus infinity and y 2 tends to plus infinity. So, what I will get is this. So, this will become, so as y 2 tends to infinity, I can neglect x in terms in comparison to y 2 square. So, I get y 2 by y 2 which is 1, and here I get y 1 tending to minus infinity. So, the two of them add up and I will get b is equal to minus mu naught I. So, that becomes a factor of 2 here by 2 pi x k cap. So, magnetic field at this point, if this distance is x. So, x is the perpendicular distance from here to this point. So, then the magnetic field at this point is pointing into the paper here, because the current is moving up, the z axis is coming out of the plane of paper, the magnetic field is minus k cap, and if you go to minus x direction here somewhere here, because x is negative here. So, field is coming up. So, the field is coming up from here and going into this plane of the paper here. So, magnetic field is curved like this, and please remember that because this has cylindrical symmetry, there is a wire like this. So, because there is a wire like this, at this point the current is going up like this. So, the magnetic field at this point is like this, magnetic field at this point is like this, magnetic field at this point is like this, magnetic field at this point is like this. So, all that at every point the magnetic field is perpendicular to the current and to this line. So, it is like this here, like this here, like this here. So, it is like a circular arc around this current carrying conductor. So, if I call r as the distance from the conductor, perpendicular distance actually, then I can replace x by r, and so if I have my current carrying conductor, if the distance is r, b vector magnitude will be nothing but mu naught I by 2 pi r. And I must know the direction of the current magnetic field by knowing the direction of the current and using the right hand screw rule. So, the magnetic field will be going into the plane of paper here, because the current is going up, coming out of the plane of the paper here. So, I can actually draw magnetic field lines. So, the magnetic field lines will look like this, and here So, that is my current carrying conductor here. So, if I look at the top view, so if my current carrying conductor is coming, if the current is coming towards me, I will have, so please remember current is coming towards me. So, I will have the current magnetic field like this. That is my current carrying conductor. So, magnetic field lines are circular circles around this current carrying conductor, and the magnetic field depends only on this distance, and it goes down as 1 by r. You may recall what we had done for an infinitely long linear charge distribution. We also calculated the electric field there, and you can compare this expression with the expression for an electrostatic field of an infinitely long current carrying conductor. So, magnetic field lines, as you can see here, form closed loops. So, let me try to draw a comparison between a line charge distribution and a line current. So, if you have a line charge distribution, for example, if this charge distribution is positive, so I have a line charge, an infinitely long line charge coming out of the plane of the paper here, and the positive. So, there is no direction, it is all positive charges. So, I will have the electric field lines will be, as you have seen, coming out like this radially out of the charges. On the other hand, if I had a current carrying conductor with current coming up, I have field lines which are closed. A very different distribution of magnetic field, and this is E field and this is B field. Here, if you take a closed surface which encloses the charge, suppose I take a closed surface like this, I will get a finite flux. If you take any closed surface here, you will get 0 flux, because as many lines are crossing in as they are getting out of the surface, and so the magnetic flux, net magnetic flux is always 0, and that is Gauss's law. That is because there are no individual magnetic charges. So, here you have integral E dot dA is equal to q enclosed by epsilon 0, and here you have integral B dot dA 0. There are no magnetic fluxes. So, let me take an example. So, suppose I have a current carrying conductor here, and suppose I assume 5 amperes of current flowing like this, and I want to find the magnetic field at a distance of 10 centimeter from the current carrying conductor. So, I have a wire which is carrying 5 amperes of current, and I am at a distance of 10 centimeters. So, B is equal to magnetic field is mu naught I by 2 pi r, that is the equation we had derived just now. So, this is equal to 4 pi 10 to the minus 7 into 5 amperes divided by 2 pi into 0.1. So, this factor of 2 here. So, that is 10 to the minus 5 Tesla, and compare this with B earth is approximately 3 10 to the minus 5 Tesla. And so, you are producing magnetic fields at a distance of 10 centimeter from the current carrying conductor, which is carrying 5 amperes current. You have some kind of a magnetic field generated at about 10 to the minus 5 Tesla. As you get closer and closer to the wire, the magnetic field will increase, but far away from the wire, the magnetic field will keep on decreasing, and you can sort of estimate the magnetic fields under, for example, high voltage lines which are carrying currents, what kind of magnetic fields will be existing under current carrying conductors, huge current carrying conductors. It is an interesting problem to understand. So, now I want to introduce a very important concept in magnetostatics, and that is Ampere's law. A very important concept of Ampere's law. Remember, in electrostatics we had first introduced Coulomb's law, which told us the electric field generated by a point charge. Then we used superposition principle to calculate the electric field produced by any charge distribution. Then we defined the quantity called electrostatic flux, and then we derived Gauss's law. Gauss's law which relates the electric flux to the charge enclosed by that surface. Now, in magnetic fields there are no magnetic fluxes, magnetic flux is always 0, the net flux through any surface is always 0, closed surface. Please remember I am looking at a closed surface, the entire magnetic flux which is entering, magnetic field line entering is also leaving. There are no magnetic charges, there are no individual magnetic poles. So, what we say is there are no magnetic monopoles, there are only magnetic dipoles and higher order poles, but not magnetic monopoles. So, we cannot derive, there is no derivation of another Gauss's law for Ampere for currents, because the magnetic flux through a closed surface is always 0. So, we have another kind of law which is called the Ampere's law, in which we do not have area integrals, but line integrals. So, now let me look at this problem which we have discussed, an infinitely long current carrying conductor. Let me assume that the current is coming up. So, I know that the magnetic field at any distance r is given by, so let me just write the magnitude mu naught I by 2 pi r, and I know the magnetic field is like this. So, if I were draw to the magnetic field lines will be like this, everywhere it is like this, everywhere it is perpendicular to this line, here it is perpendicular to this line, at this point perpendicular to this line. So, it is circling around the wire and it has the same magnitude all across. Now, let me calculate this quantity B dot dl over the closed loop. So, I start from some point, calculate for the entire loop. Now, please note that the magnetic field is always parallel to the dl vector. So, dl vector here is like this, B is parallel to dl vector, here dl vector is like this, B is parallel to dl vector, here dl vector is like this, B is parallel to dl vector. So, this is nothing but B dl, and B is nothing but mu naught I by 2 pi r into dl. So, as you vary the point of integration, r remains constant. So, I will get nothing but mu naught I by 2 pi r into integral dl. Integral dl is the total length of this path, which is nothing but 2 pi. So, this is equal to 2 pi, the 2 pi r circumference of the circle. So, this is nothing but mu naught I. So, what I have shown is for this case B dot dl mu naught I. So, integral of B dot dl gives me mu naught I, and this is for a path which I have taken a circular path around the current carrying conductor. So, I have taken an infinitely long current carrying conductor, then I calculate I have calculated the magnetic field, and then I calculate an integral B dot dl around this current carrying conductor on a circular path with the current carrying conductor to be the center of the circle, and I find n value of mu naught I. Now, what happens if I have another path, some other path which is not circular around this current carrying conductor, but some arbitrary path. So, for example, I will take so magnetic field is always perpendicular to this, but it is not along. So, here magnetic field may be in this direction, here the magnetic field is like this. At different points magnetic field is always perpendicular to the line from this point to this point. Well, the dl vector is like this here now, and B vector is here, and if this angle is phi. So, let me draw a figure again here. So, this is at this point the current element is like this, the magnetic field is here, dl vector is here, this is phi. Okay, so, I need to calculate, I want to calculate this quantity. So, I will show you that this is still equal to mu naught I, irrespective of the shape of the curve which is encircling this current carrying conductor, and I will do this in the next class. I will show you that the total integral B dot dl over a closed path is always equal to mu naught I, where I is the current enclosed by this path, and we will generalize this to more interesting problems, and that is this is what is called as Ampere's law. Now, before I finish, I want to just give you a problem. I want to just leave a problem here. So, consider two parallel infinitely long current carrying conductors. So, you have one current carrying conductor like one conductor like this, another conductor. So, let me assume the currents are in opposite directions, same current, but in opposite directions. So, I want you to find so let me draw like this. So, if I look at from the top, I have this current carrying conductor here, another current carrying conductor here. So, I want you to calculate the magnetic field at this point P and another point Q on the equatorial plane. So, what is the magnetic field? So, this is not the point here, B at P and Q. So, use the formula we have derived. You can calculate the magnetic field because of this current carrying conductor, you know the magnetic field because of this current carrying conductor. So, calculate the magnetic field because of these two, use superposition principle and calculate the net magnetic field here and here. So, the two wires are like this, one carrying current up and the other carrying current down, and so the problem is to calculate the magnetic field here and elsewhere on this equatorial plane. Thank you very much.